Now we're going to do the second kind of portion of this angular momentum and torque problem. I'm going to have a different scenario. I have an ice skater here, 60 kilogram ice skater, coming in, and he's on a completely frictionless ice. He comes in with an initial velocity of 2 meters per second, and there's a pole on the ice skating rink, and around the pole there's some chain or rope, and then the rope is sitting on the surface. And let's say the initial distance here from the center, and let's say the initial distance is 5 meters. Okay? So then what happens is he grabs onto the pole, so he just kind of quickly goes down, grabs onto the pole, and then just goes along with the rope until the rope starts to go around the pole. Okay? So he grabs onto the rope here, and then it goes around. He kind of starts spiraling in. This is similar to the previous case where the mass started spiraling in. So and let's say he ends up at 2.5 meters. Okay? 2.5 meters. Half of his original distance from the pole. So he keeps going around until he ends up 2.5 meters. Right now, don't worry about what the diameter of the pole is. How many times does he have to go around to end up halfway? So let's just say that's not even an issue at this point. The pole has some diameter. Okay. So once he ends up halfway, he lets go of the pole. He lets go of the rope. Okay? He lets go of the rope, and then he wants to continue in the same direction that he came in. So he wants to go like this. Tell me what the final velocity is. The problem is kind of set up to make you think like it is exactly the same as the previous problem. So if you don't give it much thought, you're likely to do this. L initial equals mv initial r initial, which equals L final is mv final r final. Okay? And so the m and the m cancel. If his initial velocity is 2, if the initial radius is 5, the final velocity, we don't know, the final radius is 2.5. Right? So V final 4 meters per second. So the unsuspecting problem solver, looking at this and seeing the previous problem about the mass going around, is going to be just lured into the trap. And he's going to say V final is 4 meters per second. And then therefore the problem might say, what's the work done? What's the work done on the object, on the person? So half times 60 times 4 squared minus half times 60 times 2 squared. And so if they put this as their answer, they've been lured into the trap and they are wrong. Okay? Here's the reason why. In this case, if you analyze the forces on the object, what does your analysis bring out? So you have a pole and you've grabbed onto here, right? Around what point are you going in the circle? Around what point? Okay? Well, you're going in a circle around the point given by the center of the pole, right? So here's the center of the pole. So your R is like this. Okay? Which direction is the force on you? Which direction is the tension? This one, right? What's the torque on the person? R crossed into F. In the previous case, we had a mass that was going around a little hole, and then the string, and then it was spiraling inward, and then you had a tension T, And then the radius, I had mentioned in that problem, I believe the radius is towards the center, but it's more exact to say the radius is from the center to the object instead of from the object to the center. So I should have said the radius is this one, r. But it doesn't really matter in this case. The torque would still have been 0, right? The torque is r crossed into F, which is 0, whether or not the r is inward or outward. So in that case, when we analyzed it really in detail, we saw that the torque is 0, angular momentum is conserved, but there is a parallel component of the velocity, right? So there's a parallel component, v perpendicular, v parallel, and therefore that's why the tension in the string does work on the object. Now, in this problem, since the pole has a certain diameter, the situation is different. You're going around this center, r is this vector, the tension T is that vector. So if it wraps around, keeps wrapping around, right? It's getting smaller. At any point, here's your r vector, here's your f vector. When you're at this point, here's your r vector, here is your f vector. So the r crossed into f is not equal to 0. So there is a net torque on you due to the rope that you're holding. So therefore your angular momentum is not conserved. Okay? Well, if angular momentum is not conserved, then how can I find out your final velocity when you're halfway? What is conserved in this case? This time kinetic energy is conserved. There's no work done on you. Look at this. Okay? Analyze the forces on you. Look at your velocity. Your velocity initially is this way, right? By the time you end up over here, which way is your velocity? Okay, you are over here. Your velocity is perpendicular. Yes, it is true that you are spiraling inward. It is true that you're spiraling inward. But the direction between your velocity and the tension in the rope is always perpendicular. This is the force. Here's the force. Okay? Perpendicular. By the time you end up here, perpendicular, force, perpendicular. The force that's exerted on you is always instantaneously perpendicular to the direction that you're moving. So does the force do any work on you? No. The string, the rope, does not do any work on you in that situation. So what's going to be your final velocity? It's still going to be 2 meters per second. So this time we can say how much angular momentum was lost. Okay? How much angular momentum was lost? L initial is equal to mv initial r initial. So 60 kilogram times 2 times 5. So the angular momentum initial is equal to 10 times 6 is 600 kilogram meters per second. The final angular momentum, mv final, r final, okay, v final is still going to be the same. So 60 times 2, and then r final is half. The angular momentum final, 300 kilogram meters per second. The change in angular momentum, 300 minus 600, negative 300. Okay? So, what is the torque on you? Torque, the average torque, is the rate of change of angular momentum. We could say the average torque is equal to change in angular momentum, negative 300, And then here I'm just doing the magnitude of the torque. So the angular momentum was lost, magnitude of 300 divided by the time. So once I knew more information about the problem, the diameter of the pole, I could calculate the time, put it here, calculate what the average torque on the person was, and that's why they lost angular momentum. So you see, with these kinds of cases, you have to analyze it very in-depthly. Which one is conserved? Kinetic energy? Which one is conserved? Is it angular momentum? And why? Why not? Right? And so look at it more in detail. So these are two good problems that you can compare and you can learn a lot from. Thank you.